Hello students. In the last module, we have seen the properties of least square estimators, that is beta 1 cap and beta naught cap. So just to revise what we have done so far is that our least square estimators of the simple linear regression line are beta 1 cap and beta naught cap, right? These were, and then we wrote them in a compact form. So this is for a data set where we have paired observations for xi and yi for I varying from 1 to n, where xi is the independent variable and yi is the response variable, right? Which we uh, assume that is coming from, which we are assuming that is a random variable and coming from a population distribution, a normal distribution with mean given by this and standard deviation sigma. So this value we can write y cap is equal to beta naught cap plus beta 1x is called the estimated regression line. So these are estimators because beta naught cap and beta 1 cap are estimators. So this is again the estimator of the y for the actual observation, right? So this is called estimated regression line. So there are some interesting properties which we have already discussed. For example, we discussed about the distribution of beta naught cap and beta 1 cap, that they are random variables with mean beta naught and beta 1 cap. If we are talking about beta naught cap, then its expectation is beta naught. And if we are talking about beta 1 cap, then its expectation is beta 1. That's why they were called unbiased estimators of beta naught and beta 1. And then we also got expressions for their variances, right? So if we have the data, then we can compute beta naught cap and beta 1 cap as well as their variances, right? So these were some interesting results we had obtained in the last module. Now, there are some other interesting results related to linear regression. In this case, let's first discuss, and this you will see, we can verify this also with some examples, but we can verify them theoretically as well. The sum of residuals in any regression model that contains an intercept term beta naught is always zero. That means residual we are defining as yi minus yi cap. So yi is your observed value and yi cap is given by the model, right? So what essentially I'm doing, I am plugging in the value of beta naught cap and beta 1 cap that I have obtained from the least square uh, minimization and at a particular x. So that can be a particular value of x1, for example. And then I compare it with the ith observation if I'm putting a value for ith x, right? And then if we subtract it, that will be ith residual. And when we sum over them I over 1 to n, or that means over the total number of observations. So n again I will write here is total number of observations. Right? So it says the first property says that the sum over all these residuals is equal to 0. So let's prove this. From the first normal equation, when we did minimization of sum of squares, what was sum of squares? Sum of squares was essentially this thing. Summation over I1 to n yi minus beta naught cap minus beta 1 cap xi whole square. And we differentiated it with respect to beta naught to obtain the least square estimate of beta naught and then put it equal to 0, the differential partial derivative, and then we put it equal to 0. So that equation gave us, if you still remember, you can recall this, and then we can also find it from here, that it will be minus 2 summation over I1 to n yi minus beta naught cap minus beta 1 cap xi equal to 0. Summation over I1 to n yi we can take on the other side. These terms will remain on one side. So if we sum beta naught n times, so it will be n beta naught cap. The second term will be just summation over beta 1 cap, summation, I'm sorry, beta 1 cap summation over I1 to n xi is equal to summation over I1 to n yi. And you know that our model yi for ith observation is this. So I can put it here on the right hand side actually. So the left hand side will be simply n beta naught cap plus beta 1 cap. So this is left hand side I'm writing summation over I1 to n xi. I missed to put caps here. So that will be equal to, and then we are replacing yi here. So that will be summation over I1 to n beta naught plus cap. This should be cap beta naught cap plus beta 1 cap xi epsilon I. So left hand side will remain like this. If I take this summation operator inside, so it will be n beta naught cap. It will be n beta naught cap plus beta 1 cap summation over I1 to n xi plus summation over I1 to n epsilon I. So you can see that these terms are equal on both sides. So they will get cancelled. So what we get is essentially summation over I1 to n epsilon I equal to 0. So that we have already proved now. The second property is that the sum of the observed values yi equals the sum of the fitted values yi cap. So yi cap are the fitted values. So that property is, if we write it, is essentially summation over I1 to n yi, that is sum of the observed values and sum of the fitted values, that is summation over I1 to n yi. So that is actually follows from here. This is just following from this result which we have just obtained, right? So this we can clearly see that if it is equal to 0, then we can write it like this. Okay. The another property is that the sum of the residuals weighted by the corresponding values of the regressor variable always equals to 0. Mathematically, summation over I1 to n xi is the regressor variable, epsilon I equal to 0. That means the residuals which are weighted by the regressor variable, and when we sum them over the total number of observations, it is equal to 0. So let's prove this also. Summation over I1 to n xi, epsilon I can be written as yi minus yi cap, summation over I1 to n xi, yi is yi cap can be simply written as minus beta naught cap minus beta 1 cap xi, right? And then this will become summation over, I can take this, expand this and multiply inside and take the summation operator also inside, summation over I1 to n xiyi minus beta naught cap summation over I1 to n xi minus beta 1 summation over I1 to n xi square. And from the second normal equation, when we differentiated this equation two times, when we differentiated this equation with respect to beta 1 cap and then put it equal to 0, what we observed, what we got was this equation, right? This we already had from the second normal equation. And you can see here also that xi minus beta naught summation over I1 to n xi minus beta 1 cap summation over I1 to n xi square is essentially this thing, right? So that means summation over I1 to n xi epsilon I equal to 0, because this is actually from the second equation as normal equation. We already got this, so we can put this value from the second normal equation and then it will come out 0. So this we proved that the weighted sum, or the sum of residuals weighted by the corresponding, so ith x is multiplied with the ith residual, then we sum them, then it will be equal to 0. Similarly, one other property is that the sum of the residuals weighted by the corresponding fitted values is always equal to 0. So earlier it was for xi's, now it is for yi caps. So that summation over I1 to n yi cap epsilon I equal to 0. So here we are um, we, we are multiplying epsilon I, or we are weighing them with corresponding fitted values of yi cap and then summing over them over the entire length of the data. What we are getting is 0. So we know yi cap is equal to beta naught cap plus beta 1 cap xi. So I can replace this here. So this will become summation over I1 to n beta naught cap plus beta 1 cap xi epsilon I equal. We are proving this, so you can leave actually this term, or we just write RHS is equal to LHS. Then we can take this beta naught and we can multiply. Essentially what we can do is that we can expand this, epsilon I can get multiplied, and then we take the summation operator inside. So beta naught cap summation over I1 to n epsilon I plus beta 1 cap summation over I1 to n xi epsilon I. Just now this we have proved that is equal to 0. And expectation of epsilon I, I'm sorry, not expectation, this also we have proved in one of the results. So this is not expectation here, this is just summation. So we have just proved this, that it is 0 from the first property, right? So this is 0 and this was also 0 from the third property. So that means it should be 0. So we can say LHS equal to RHS. That means summation over I1 to n y cap epsilon I should be also equal to 0. So these were some interesting properties of these least square estimators. Now one problem is often comes that estimation of sigma square. So sigma square is the variance of the yi values at each value of x. So often we do not know sigma square beforehand. We have to estimate it from the data. Usually we have to estimate it from the data. So that sigma square will be actually, we will be estimating it from the sample of the data, as we were estimating beta naught cap and beta 1 cap. And we hope that this estimate from the sample of sigma square is a good representation that what actually sigma square should be for that larger population. So to estimate this, how we estimate this, we define sum of squares of residual. So we have also defined this before. So that is summation over I1 to n epsilon I square. So I again repeat, if I have not written explicitly summation over I1 to n, the summation sign implicitly implies that summation is overrunning I from 1 to n, where n are number of total number of observations. So this sum of squares can be written as summation over I1 to n yi minus yi cap, where yi cap is the fitted value, that is beta naught plus beta 1 cap xi, right? So that we are writing here that summation over I1 to n yi minus beta naught cap minus beta 1 cap xi whole square. And we also know that the value of beta naught cap from the least square estimates is beta naught cap is equal to y bar minus beta 1 cap x bar. So we will replace this also here in this equation and then try to expand this expression what we have here for sum of squares of residuals. So we sometimes say it's simply sum of squares, or sometimes specifically we can say it sum of squares of residuals. So summation over I1 to n yi minus y bar minus beta 1 cap I think it should be one term should be beta 1, yeah, one term should be beta 1 xi, and the plus term I'm writing later, so it will be beta 1 cap x bar, because this is already 1 minus, so it will become plus this term. Then what it becomes, summation over I1 to n yi minus y bar minus beta 1 cap can be taken common. It will be xi minus x bar whole square, because there is whole square term is there. Then we can expand this whole square term, and you already know very well how to do that. That summation over I1 to n, this term yi minus y bar whole square, and I'm taking the summation operator also inside. It will be beta 1 cap square summation over I xi minus x bar whole square minus twice of beta 1 cap summation over I1 to n xi minus x bar multiplied by yi minus y bar. So these term here, this term can be written as SYY, which we have discussed before. You must be thinking, no, this looks different. It's not SYY, but we can show that it is equivalent to SYY. Similarly, this term can be written as SXX, and this term can be written as SXY. So I will just show for one of them. So let's do it for this one, that how it belongs to SXX. And then we know beta 1 cap is sxy by sxx, that we have done in the previous module. So but first let me show that how they are becoming sxx. So this is just some sort of rough work we are doing here. Summation over 1 to n xi minus x bar whole square. Then we can assume it for everyone. So I will just show for only one term. So summation over I1 to n, we can open this xi square plus x bar square minus 2xi x bar. Now I take the summation sign inside, summation over I1 to n xi square plus summation over I1 to n x bar square minus 2x bar summation over I1 to n xi, right? So this will be summation over I1 to n xi square plus, since this will be a fixed value, so we can just write it nx bar square, because it will be summed n times. And from the definition of this, from the definition of x bar, we know that it is I equal to 1 to n xi. So this term can simply be written as n x bar. So I'm just writing this minus 2 n x bar square because 1 x bar was already there. So this will become summation over I1 to n xi square minus n x bar square. So you know summation over I1 to n, we have actually got the Sxx. Summation over I1 to n xi whole square. So that is I equal to 1 to n xi square minus 1 by n summation over I1 to n xi whole square. So that was Sxx. Similarly, it will be Syy and for the cross term xy also, right? So that is how we wrote them like this: Syy Sxx beta 1 cap square minus twice beta 1 Sxy. And we know that beta 1 cap is equal to Sxy divided by Sxx. So we can replace this here. Then we are replacing it here totally. So this will become sum of squares of residuals Syy plus beta 1 square Sxx minus twice beta 1 cap Sxy. So Syy plus beta 1 square Sxx is already there. And this can be written again in terms of beta 1 cap Sxx because beta 1 cap was Sxy divided by Sxx. So Syy plus beta 1 square Sxx minus twice beta 1 beta 1 is already there, so it will be minus twice of beta 1 square Sxx. So sum of squares of residuals will essentially become, because one of them will go out, so it will become Syy minus beta 1 square cap beta 1 cap square Sxx. So that is our sum of residuals, sum of squares of residuals in terms of Syy and Sxx, and it depends upon beta 1 as well. Now let's compute the expected value of this. That what will be the expected value of sum of squares of residuals. So this can be computed as expectation of S sum of squares of residuals. So we can take expectation operator inside expectation S. So it's simply S. So no double S is here involved. So it's simply single S. Syy minus expectation of beta 1 square, beta 1 cap square Sxx. So again, it's simply single x, right? Just to differentiate it from the sum of squares of residuals. For that, first we would need to compute expectation of Syy because we need to compute this, and then we will compute the expectation of this. Then we can compute expectation of sum of squares of residuals. So expectation of Syy, so this will be simply Syy will be equal to expectation of summation over I1 to n yi minus y bar whole square, because just now we have proved that this is Syy, right? So just now we have proved this. So you can expand it first and then take the summation operator inside, right? So I think I have already taken one summation operator inside, but yeah, summation operator I have taken inside, but not expectation operator. So we first expand it and then take the summation operator also inside. Summation I over 1 to n yi square plus summation over I1 to n y bar square minus twice summation over I 1 to n yi multiplied by y bar. And then this is the same term here. And we know that y bar is summation over 1 by n summation over I 1 to n yi. So I take then expectation operator also inside, and I'm just writing yi square is like this, as we have seen here, summation over I 1 to n y bar square, because this can be a fixed value. So it will be, when we are summing it over n y bar square, and one of this term y summation over I 1 to n yi can be written as ny bar. So it will be simply minus twice ny bar square. One of them will get cancelled, as we have seen before. So it will be expectation of syy will be expectation of summation over I 1 to n yi square minus expectation of ny bar square. Right? Now, again, invoking the independence of yi values, I can take expectation operator inside the summation operator. So that will be summation over I 1 to n, expectation of yi square minus, because n is a fixed number, so it is total number of data points, so n expectation of y bar square. Now we need to compute these. Then we can compute syy and this value. So we know from that our model is yi is equal to beta naught plus beta 1 xi plus epsilon I. So expectation of yi is essentially beta naught plus beta 1 xi, and variance is sigma square. So that we can see here, first we need to compute expectation of yi square. So in order to compute expectation of yi square, we use the formula of variance. So this is for any random variable x. It is expectation of variance of x is equal to expectation of x square minus expectation of x, and then it's a square. So using this formula, I can essentially compute this term. So I'm computing expectation of yi square is equal to variance of yi plus expectation of yi, then it's a square. So expectation of yi square is variance of yi we know is sigma square, and expectation of yi we know beta naught plus beta 1 xi whole square, right? So this is expectation of yi square. Using the same, we can compute the expectation of y bar square, because we need to compute expectation of y bar square also. So it will be using the same formula, the variance of y bar plus expectation of y bar, then the square of that. So variance of y bar we have seen already in the previous module that it is sigma square by n, and this will be expectation of y bar whole square, or the square of the expectation of y bar. Expectation of y bar can be written as 1 by n expectation of, because y bar is summation over 1 by n summation over I 1 to n. So I can take, again invoking the independence of yi's, I can take expectation operator inside of the summation. So that will be expectation of y bar will be 1 by n summation over I 1 to n expectation of yi, and expectation of yi is again this value. So it will be 1 by n summation over I 1 to n beta naught plus beta 1 xi. So this is a fixed value. So if we sum it over n times, it will be beta naught n. 1 by n is outside, beta 1 beta 1 and summation beta 1 by n is there, 1 by n summation over I 1 to n xi. So expectation of y bar is beta naught plus beta 1 x bar. So summation, expectation of y bar square will be sigma square divided by n plus beta naught plus beta 1 x bar whole square, because it has to be its square. So we have computed these two, expectation of y bar square and expectation of yi square. So expectation of SYY, which is this, can be written as summation over I1 to n expectation of y I square minus n expectation of y bar square. So expectation of SYY will become, when we substitute the values we have just computed for these two, sigma square plus beta naught plus beta 1 xi whole square minus n sigma square divided by n plus beta naught plus beta 1 x bar whole square. For this one, if we sum it over n times, it will be n sigma square. We can take summation side inside, summation operator inside. Summation over I1 to n beta naught plus beta 1 xi whole square. Here also it will be 1 n will be cancelled. So it will be minus sigma square. We will take minus sign inside, minus n beta naught plus beta 1 x bar whole square. So this will be essentially sigma square will come common between this and this. So it will be sigma square n minus 1, and this term will be this summation over I1 to n beta naught plus beta 1 x by whole square minus n beta naught plus beta 1 x bar whole square, right? This term. Now I leave this for you to prove as an exercise that expectation of SYY will essentially become sigma square n minus 1, this term, this term, this is same, that I leave this for you to prove as an exercise that it will become beta 1 square summation over I1 to n xi square minus nx bar square. This you can prove. So it's not difficult to prove, and it's essentially Sxx. We have just now seen that it is essentially Sxx. So expectation of Syy is sigma square n minus 1 plus beta 1 square Sxx, right? Now, expectation of sum of squares of residual. So this term we have computed, it is expectation of Syy minus expectation of beta 1 cap square Sxx. So expectation of beta 1 cap square Sxx is equal to Sxx, because it will be a number or a constant. Then we can write expectation of beta 1 cap square, right? So we are looking for this term now, that what will be the value of this term. So for first term, we have already found from here. One thing, yes, I think that is fine. So Sxx has come outside. We know that expectation of beta 1 cap is beta 1, and variance of beta 1 cap is sigma square divided by Sxx, that we have proved in last module. Why we will need them? Because we need to compute expectation of beta 1 cap square. So again, we have to use this formula of variance. So I'm using this and directly writing expectation of beta 1 cap square is equal to variance of beta 1 cap plus expectation of beta 1 cap and the square of it, right? So I'm using here the variance formula. What is that variance formula? That variance formula is variance of x is equal to expectation of x square minus expectation of x and then x square. So that formula I'm using, right? I think this is right. Variance of x expectation of x square. Yes, I think that's correct. And then we know already variance of beta 1 we have just seen is that sigma square divided by Sxx, right? This we have just now seen. And or in the actually we proved it. I have just written here, but we proved it in the last module, and expectation of beta 1 cap we know is beta 1 square, beta 1, so its square will be beta 1 square. So we need this expectation of beta 1 square sxx. We can write this because we needed this. This will become sxx because this is sxx multiplied by sigma square divided by sxx plus beta 1 square plus beta 1 square, right? So we have written this thing like this. So 1 sxx is coming from there. So expectation of beta 1 cap square sxx will be equal to, if we take sxx inside, sigma square plus beta 1 square multiplied by sxx. So finally, now this value and the value we got for expectation of syy, if we plug in them here in the expectation of ss or sum of squares of residuals, what we will get? Sigma square n minus 1, this is here, plus beta 1 square sxx minus for the second term minus expectation of this term sigma square minus beta 1 square sxx. So one thing is to note that beta 1 cap is the estimator and beta 1 is the true value of beta uh, of the slope. So expectation of sum of residuals, sum of squares of residue is sigma square. 1 sigma square is also here, so it will be sigma square n minus 2. This and this will get cancelled. So we can clearly see, or we can write this, that expectation of sum of squares of residual divided by or by n minus 2 is equal to sigma square. We can say that sum of squares of residuals by n minus 2 is an unbiased estimator of sigma square. So as I said, in general, sigma square is not available, but we can compute sum of squares of residuals. Sum of squares of residuals are simply these values, right? These values are sum of squares of residuals. So the expectation of these values, or we can say that expectation of sum of squares of residuals divided by n minus 2 is a unbiased estimators. So often we will use this to represent or to compute the sigma square. So this term sometimes is called mean square residual also, MS residual. Sometimes this is also referred as mean square residuals. So that's why I'm writing it as sigma cap square, just to reflect that it is an estimator of the true sigma square, right? So SS, or sum of squares of residuals divided by n minus 2, is an unbiased estimator of sigma square, because sigma cap square is computed from the regression model, because here regression model is coming into the picture, which you have fitted beta naught cap and beta 1 cap. This should be cap here. So because it's a model dependent, we are computing it from the model. So this estimate is a model dependent estimate of sigma square. It's not the actual or the true estimate of sigma square, but it's a model dependent. So it depends upon how good your model is fitting, right? Often we need this estimate of sigma square. You must be thinking, why do we need about this? But we need to assess the goodness of fit of the regression model sometime, that how good is our regression model. So for that, the estimation of sigma square is needed. Often you will need it for hypothesis testing and for getting interval estimates to certain parameters of the regression model. So it's a important, pretty important parameter. Sigma square is pretty important parameter in regression analysis. And in reality, in practical situation, we compute it from sum of squares of residuals, divided them by n minus 2, right? So this module we stop here in this module. We have seen here in this module four important properties, more important properties of least square estimators and regression analysis, linear regression analysis. And then we finally prove that sum of squares of residuals divided by n minus 2 is an unbiased estimator of variance of the response variable, that is sigma square, right? So we stop here. Thank you.